our next speaker in the series of MoD, Mathematics of Data Center lectures. So today we have the great pleasure of having with us Sebastian Peitz. As you see, he's a young, but still, as you will see, extremely prolific scientist. He got a bachelor and a master in Athens. He has been since then in Paderborn University, where he has been a junior professor. Recently, he got an offer that he accepted to become a full professor at the Technical University of Dortmund, where you can meet him starting in next October. Yeah. So congratulations for all these achievements. And his recent work has been very much on the interface between control sciences and machine learning. And yeah, actually, I think it was maybe, I don't know how I got to know about his work, but I found it particularly interesting with some substantial connections with some of the topics that we are working in our group as well. So I thought that it would be a great lecture to listen. And Sebastian was kind enough to accept and come visiting us for the occasion. So yes. Now is your time. Yes.
Okay, thank you. First of all, thanks a lot, Enrique, for the kind introduction and also the invitation. It's a very great pleasure to be here. Yes, and this is a rather lengthy title, but maybe we can jump over this and dive right into what I want to do. So my overarching goal in my research is to study complex systems, mostly governed by partial differential equations. So potential applications, fluid mechanics, aerodynamics, we're starting to look into coupled physics, magnetohydrodynamics, where you have even more complex physics, or Rayleigh Benard convection, where you have these buoyancy-driven flows. So all of these systems are governed by PDEs, so state is dependent on space and time. And standard numerical discretization schemes like finite elements, finite difference can usually be used, and they are super accurate and also efficient by modern standards. But still, if the complexity becomes this high, then they tend to be very expensive to simulate. We need high performance computing and topics like this to do so. And even more problematic is this if we want to use the model several times, determining feedback laws or solving optimization problems, so classical multi-query contexts. So this is true for two topics that I would like to cover today, which is the control case using model predictive control on the one hand. So I'm using a model to solve an optimization problem online, and reinforcement learning, where I try to train an agent that learns by trial and error with the system how to optimally influence it. And so the aim, since these are so expensive, is to exploit structure in the system to learn models or learn control laws in a more efficient manner. And what I mean by structures is something I'm going to talk about in quite a bit of detail. Structure also means I can use a learning algorithm that specifically is tailored to dynamics. And this would be a simple structure. I know that I'm dealing with dynamic systems, but we are also going to talk a little bit about symmetries. Can I use additional knowledge on my system that it is even more efficient to solve it, or to solve the learning problem, and then use these models further on? Okay. So, but before we dive in, it's very cool that I'm in Erlangen, and particularly in the Felix Klein building. And so, a small reference here, there's a very popular area of machine learning nowadays that is called geometric deep learning. And so the authors of this, it's a book, not yet published, but it's a rather substantial book about this topic. And they argue that they have been heavily influenced by Felix Klein and his idea of, using symmetry as an overarching concept for many branches of mathematics. And they don't claim to make equally substantial contributions, but they say that they have been heavily inspired by this mindset, right? To use symmetry concepts in connection with machine learning to show that, actually symmetries play a vital role in many areas of learning as well, right? And so I find this really cool because of the location, but also to see that this is something that is rather old, 150 years, still has a significant impact on topics that Felix Klein would never have thought of, at least I guess. So, but this is the statement, right? Geometric deep learning. And I'm not going to do geometric deep learning in that much detail, but I'm going to use this idea on symmetries and hopefully be able to increase the efficiency. Okay, but before we do so, this is the setting I will study, rather abstract, and it's the computer science notation, right? So I do have, instead of a state, usually X or something, I use S for the state variable. I use A for my action, which we know as control U oftentimes in dynamic systems. But nevertheless, it's just an abstract formulation of a partial differential operator. I don't worry with the boundary or initial conditions at this point. It's just to show I have a PDE like the fluid mechanics problems, heat equation, whatever you can model in this way. And I'm right the way going to discretize this in time, because this is what we use in reinforcement learning, for instance, these episodic behaviors. Or if you discretize a model predictive control scheme, you can go to the discrete level right away. So this capital T simply denotes my flow map that predicts one time step ahead. And using this, I can formulate an optimal control problem in discrete time. So I have the dynamics for my state S, which is the PDE state. So it's still a function of space. And I have this objective function that depends on the entire state and action trajectories. So it's some sort of stage cost, minimizing the distance to some objective or a reference trajectory. Okay, so now I want to use a feedback control rule to stabilize my system or steer it in a certain direction. And I want to use both these approaches that I mentioned earlier, model predictive control and reinforcement learning. And actually, I would like to show you that there are two sides of the same coin, essentially. Okay? So if we think about model predictive control, then we usually have this real system, what we would call a plant sometimes. We measure the state or some function of the state. For simplicity, I'm just saying I'm measuring the state. And then I'm using in my controller this this open loop optimal control problem. And once I've solved it, I apply the action or the first entry of this action to the real system to close the loop. And then I repeat this procedure to obtain really a feedback behavior that is more robust than open loop control. And so if the model is expensive, then what we do to accelerate it is we use data to learn a model, right? So this big T here is what is usually expensive because it's a time step of my Navier-Stokes equations, for instance. So I need to really compute a lot to solve this. So the goal would be to replace this T by some model that I've learned from data, offline maybe, and then solve the OCP online, which is much faster, given that I have a more accurate or a faster model. And now we have reinforcement learning on the right-hand side. You see the picture is actually quite similar, right? So it's the same idea. I have a real system. I measure the state or a function thereof. And then my agent here simply is a mapping from state to action. So it's directly the feedback law, what's called a policy in reinforcement learning. It's just a function mapping state to action. And if I have a good approximation of the optimal function, then I have a good feedback controller. And so whereas the challenge on the left-hand side is, well, this can be very expensive to solve the optimal control problem online, but you have a challenge to solving it faster than real time. On the right-hand side, we have the problem that, well, it's quickly to evaluate. This tends, usually pi is modeled by a neural network, or maybe even a linear function approximator, so something that is quick to evaluate. However, the training can be super, super expensive. And so these are the challenges: real-time capability or sample efficiency. And so what I would like to do is to split my talk into two halves, talking about how to find models first for MPC, and then how to use symmetries directly in reinforcement learning to use my system knowledge to reduce the training data that I need. Okay, so let's start with MPC. And with this example that I'm going to use many times or related problems. Okay, so you see the Navier-Stokes equations. I have a fluid that enters from the left and hits this cylinder and creates this vortex shedding pattern. Right? And so this is now the lab situation, but you can think of this as islands that are hit by cloud patterns. And you see that these are satellite pictures from NASA where you see that these vortex trees actually form in reality as well. And now I would like to control the system, right, by rotating the cylinder. Well, of course, I cannot rotate the island, so this here where the analogy stops, but I would like to do this in, let's say, an aerodynamic setting or something like this. So what I can argue is actually what we usually want to do is we want to influence the forces on this object, right? The lift force maybe, or the drag force. So if I use finite volume to discretize the state, I get 66,000 degrees of freedom every time step, but I actually don't care about this. I only care about the forces that I want to influence. So one thing you could do is, and what people have been doing a lot in recent years, is to simply use deep learning and say, I don't care about anything. I measure data, I train a model, and let's go. And this is something you can do, right? Here's the architecture doesn't really matter. What matters is you have the measurement, which I will call Z here, which is lift and drag at time instance K, and the corresponding control input U, or action A before. And then you have some recurrent neural network architecture that predicts the next time step. And if you have something like this, then you can formulate on this an objective function, and you can backpropagate to calculate derivatives, and then you can solve this open loop control problem for MPC, as I said before. And if you do so, then you can do, for instance, lift tracking rather easily. Okay, so this looks convincing, but we have two challenges. First of all, it's very data hungry. So you need tons of training data, tons of offline simulations to actually train such a neural network. And we have no guarantees at all. So it's really, it works apparently, but well, I don't know who would enter a plane steered by such a neural network, right? It's rather unreliable, I think. And this is why people don't do it. And so here comes the first, let's say, knowledge exploitation. Let's use something that is more tailored to really dynamic systems. Yes, and what we're going to use is this idea of the Krugman operator, which I will introduce rather, let's say, hopefully pictorially. It's an idea, it's almost 100 years old. It was introduced by Bernhard Krugman, who is the name giver, and John von Neumann in the 30s, because this was the time where quantum mechanics was really popular. Oh, it's still today, obviously, but became really popular. And then you have all these linear operators acting on observable functions. Right? And the idea was, okay, let's use these ideas, these operator theoretical concepts, and apply them to classical mechanics as well. Okay? So they said, let's define this operator that does not act on the system state, but it acts on an observable function, which I'm going to denote by F. Okay? So here's an example. You have the sea surface temperature of the Earth, maybe, and instead of measuring or taking the entire state, which be the temperature distributed in space and time, you measure you put sensors in the ocean and measure the temperature at these locations. And so F is not the sensor data, but F is the function mapping the ocean temperature to these sensor data values, right? And what I'm denoting by Z would now be the temperature at these blue points. And then you can define this Krugman operator as a composition operator that does not act on the state, but it acts on the observable function. Right? So it acts on a function space. However, it acts in such a way in a linear manner. Right? So the idea is, whereas the original system, T of S, might be a nonlinear flow, this composition operator simply, what it does is it maps forward in time this observable function. And so what you get as a result is the observable function evaluated at a consecutive time step. So you get a linear, infinite dimensional system that maps forward this observable function. So if you plug in today's temperature distribution of the ocean, after applying the Krugman operator, you will get the temperature measurements tomorrow. And so if you can approximate this operator, you get some nice idea of how to propagate these observable functions. This is the idea. So it's linear, but it's infinite dimensional because we act on functions. And so just one brief comment here, maybe this does not simply mean linearization, because in practice, people tend to use this as a linearization scheme, and it works very nicely in many situations. And people have been doing this in system identification for a very long time. But the idea is quite different. So let's take a very simple example. Let's take the dynamic system. So we have a scalar state. Square root is the system, the map, and the observable function is raising this to the third power. So if I apply the definition of the Krugman operator, so taking the observable at the next time step, this is just the Krugman operator composed with this. And so if I plug in all the rules, what I get is square root or s to the power of 3/2. So what the Krugman operator does, it is a linear operator which transforms this observable function. So it's not easily said, well, it's a linear mapping. It's more complicated, and this is why we need to be careful on how to approximate it, right? There's lots of discussion what you can actually do and what is beyond limits. Maybe we can talk about this later a little bit. All right. And so how do you do this in the simplest way possible? And you will immediately recognize there's a large gap between what I just said and what we're doing here, or others are doing also. This is what's called the dynamic mode decomposition. So the idea is pretty straightforward. You collect data from a time series. So these are snapshots of the cylinder flow at consecutive instances in time. And then you arrange them in these snapshots matrices. So every column is one very large flow field vectorized. So the grid nodes of the finite element mesh, let's say. And then you have this S hat matrix, which possesses basically the same information, only shifted at one time step. And what you can say then is, let's assume there exists a linear operator, so a matrix, that maps S to S hat in the best possible way. Okay? So what we get is a very simple linear regression problem. So minimize the error between A mapping S forward and S hat. And so if you minimize this, it's a linear regression problem. And what I'm going to say is that this is a finite dimensional approximation of the Krugman operator, because you have learned, let's say, by regression, a linear map that maps forward the state in time. And what you can do then, this is the benefit why people are so happy to use this, you can do all sorts of linear analysis studies on this matrix, right? You can decompose it into eigenvectors and eigenvalues. And these eigenvectors, if you do the inverse of the vectorization, look like these. So you have these sort of modes, and the eigenvalues associated with them give you information about growth or decay and about the frequency with which these oscillate. So you can think of this as very loosely as a, let's say, generalized Fourier transform. You decompose your state into different modes that oscillate with unique frequencies. However, now you might say I've cheated quite a bit, right? Because I said I took a long explanation to say that it's not simply a linearization, and this is what I've done here. Right? And so obviously there's a gap, and so this assumption of linearity breaks down very quickly. So simply taking the state and mapping it forward cannot work for non-linear system, basically. So what we can do now is we can use, and this is why the Krugman operator has become so popular again, I would say, is that we have made a lot of progress in terms of approximation theory and function approximation. So what we can do is a standard Galerkian approximation of my function. So I'm going to say my function f is composed of a basis psi I, and I have these coefficients ai, and so I'm introducing a finite dimensional subspace of this function space that I'm considering, right? F lives in L2, let's say, and this is now a subspace of L2 spanned by these functions. So everybody in the room will know this, right? You take a Fourier basis, for instance, and you can approximate any function as long as you take sufficiently many of these basis functions. And this is the idea, basically. And what you do is you change the regression problem not to using S and S at the next time step, but this version with the Galerkian basis for my function space F. And then you can see this matrix K, and it's a different matrix than before. The dimensions are different, obviously. This is now a much better approximation of this Krugman operator, right? Because you can say it's sort of what I get is the Galerkian projection of the Krugman operator onto the subspace spanned by this dictionary of basis function that I selected, right? And then there's theory telling us, right, if the data goes to infinity and you measure it from some appropriate measure according to the dynamics, you have convergence to the Galerkian projection, and you can talk about, if this dictionary grows infinitely large, you have actually convergence to the true object. And people have started looking at finite data error bounds more recently as well. So there's more theory, I would say, than there is for neural networks. And this is why this, in my opinion, is more useful. Of course, there are also limitations. One can talk about, boundedness of this operator and so on. But my way of thinking about this is, or the practical way of thinking about this is also, and there's mathematically they are quite distinct, but the idea, I think, is related. What you do is you have a complicated nonlinear system, and then you introduce this basis psi, and you introduce many basis functions, and so you lift it into a higher dimensional space. And this has been known for a long time in the machine learning community for classification, for instance. Okay? So you lift your measurement data here is, the goal would be to separate the red squares from the green circles, and you cannot do so by a linear function on the left-hand side. But now that you lifted it, you can find a plane that separates it. And so you might think of this from a practical perspective, while the Koopman operator does a similar thing, right? You lift your data long enough, and in the end, you hopefully find a linear system in this lifted space. And so this is why people are very keen on using it, because once you have found this linear, this model, the matrix, you can do all sorts of linear tricks with it for control and for analysis as well. All right, and so here's the picture that you can have in mind maybe. So on the left-hand side, we have our dynamic system, ODE or PDE, can also be an SDE, mapped forward by this flow map T. And then we have this Koopman operator, which is this composition with the observable function that gives you the value of the observable at the next time step. And then this is why it has been more popular recently. We have these numerical tools at our hands that we can find finite dimensional approximations using simple linear regression. So training is very efficient. And we have theoretical statements. There's more to be done, I guess, but we have quite a few statements at our hands already now. Okay, so back to control. How can I use this? Because all I've done until now was an autonomous system. You know, I have a time series, I have no influence over it, and I want to use maybe the matrix to replace my Navier-Stokes solver for control. And so what I will do here is, discuss a few points how you can do it. So the simplest trick, which has been done almost instantly when it came out, was to say, okay, I'm not considering my state, the observed state Z on its own, but I simply add the control and treat this augmented vector as my new state on which I can do regression. Okay? And then what you can do is you map forward this vector in time, so psi of sk to psi of sk plus 1, or tau is my index here, and u tau to u tau plus 1. But the mapping in the control doesn't make any sense. So what you end up with is a simple linear regression problem that maps this right-hand side of a linear system to the next time step. So what you get is sort of this type of linear system. And I mean, you may immediately recognize this seems to give you a dynamic system, but we have left the Koopman domain quite a bit because this looks straightforward like linear regression or system identification as it has been known for quite some time, I would say. However, if you do it, you can use LQR control, right? So you have a linear system, you formulate a quadratic cost function, so you can solve the optimal control problem by solving a linear system, which is much, much more efficient than using an iterative solver, which contains, let's say, the Navier-Stokes equation as a constraint. However, well, as I said, right, this is more of a heuristic setting, I would say. You cannot guarantee that you get a model that follows what the original data should do. And if you augment the state, you see that you basically, if you say, I want to have equidistant sampling in my data space, then this augmentation leads to an exponential increase in the dimension of my measurement space. Right, so there are alternatives, which I'm not going to talk about in too much detail. One can again show that because this operator is a linear operator, you can carry over control-affine properties of the original dynamics to these operators. And so linear interpolation between different operators measured at different fixed control inputs is possible, or you can go back to switching between different operators. So these are just two options to avoid this exponential growth. And these are also, well, favorable, I would say, because you can leverage all these theory results for the autonomous case. All right. So now we have gotten a bit of an idea. Let's see an application. Right, so what I'm going to do here is, again, the Navier-Stokes equation as I had it before. And I'm defining my observable function as the function taking the flow field and measuring the lift coefficient, the drag coefficient, so the force acting on the cylinder, plus I'm placing 6 of these measurements in the wake where I measure the vertical velocity. So I have an 8-dimensional measurement. And now I can learn a surrogate model for these measurements, right, which depends now on my control input, right? I'm glossing over details a little bit, but you can say, I'm learning data for rotating left, for not rotating, and for rotating right. These are the 3 different versions. And then I'm asking, well, which should I apply to do so? Right? So what I'm doing is I'm taking data, a long time series with different actions. I'm plugging these into my eDMD algorithm. I define a dictionary that lifts these 8 measurements into a 40, 50 dimensional space, simply by taking monomials up to degree 3. And then I have this optimal control problem, which means, you know, take this linear dynamical system subject or minimize the distance of the first entry of my measurement to the reference lift trajectory. So I've replaced my Navier-Stokes solver by this matrix vector multiplication in hope that it does something as I would like it to do, right? And let me be clear, there's no guarantees here, but MPC is a very robust algorithm because you don't do this offline. You do it multiple times and only apply the first part of the control that you've computed to the system. So if the model is not very accurate, it doesn't hurt us in MPC. In open loop, you have to be much more careful on modeling. In the feedback MPC setting, you know, nudging your system in the right direction is usually quite helpful. And so what you see here is on the top, you have the Navier-Stokes system, and on the bottom left, you have what our Koopman model basically sees, right? So you have these 6 colored measurements, which is the velocity in the wake, and then you have in red the lift trajectory and black the drag trajectory. And the stars is the sinusoidal shape that I would like to track. And on the right-hand side, you see the cylinder rotation, which is visualized by this piece of cake and a cylinder in the top. And so you see that actually we achieve rather nice tracking of the sinusoidal curve, except in places where we hit the control bounds. So we have replaced a complex nonlinear solver by a data-driven model that takes just sensor measurements. It's not a perfect model, but it's sufficiently accurate to use it in MPC. And of course, you accelerate the MPC loop by several orders of magnitude because, well, obviously, matrix vector multiplication in 40 dimensions is much, much cheaper than using an iterative or implicit solver for the PDE. Okay, so where does this leave us? Well, I started with Felix Klein and the Erlangen program. Then I deviated a little bit to dynamic assistance, but maybe we can use this idea from the beginning in a very simple manner to be open. But maybe we can use it, okay? So the idea is, can we do more than just learning, taking some measurements and fitting a matrix? Can we use more system knowledge to get even better, okay? And so what we are going to use as an example is the Kuramoto-Zivashinsky equation. So it's a very, very well-known nonlinear PDE, which sort of models the propagation of flame fronts. But the details don't really matter. It's such a nice example because this is the non-dimensional version. I will have the dimensional version later as well. So there's parameter mu. And depending on your choice of this parameter, it's a very, very simple system. It looks like the wave equation. If you increase it, it gets more complicated to this bimodal behavior, and it becomes fully chaotic after some value for mu. So you can study really nicely the complexity of the system and then how your model behaves. Okay. And so what we see is there are apparently symmetries in the system, right? So there's a flip left-right or top-down in the way I've drawn it here, symmetry in terms of space. And also there's a continuous translation in space, right? So if I initialize my PDE differently, you know, I shift it and then apply the flow map, I get the same as if I apply the flow map and then shift the resulting state. So equivariance with respect to shift. And the question is now, can I use this also for my modeling with Koopman operators, right? And so this is now hand waving, but let's say if we consider measurements, point measurements in space, so I measure my PDE at a certain point in space, then due to this equivariance, it shouldn't matter which point I measure, right? So there should be some sort of equivariance. All points should be the same basically under this symmetry, the symmetry group I'm considering here. So how can we use this? This is now the equation again, and we will simply use our standard dynamic mode decomposition here. So we have this true trajectory for the very simple case of this traveling wave now. It's almost linear, so it's very easy to use DMD to learn the model. Basically, you learn something like the wave equation, which is linear from the first place. But what you do is you measure all points in space, so the final element grid. Let's say it's 64-dimensional, and then you learn a 64 by 64 matrix that maps forward the state in time. And because it's close to linear behavior, we have very good accuracy without doing any tricks. And now what I'm going to do is I can say, well, basically there is a symmetry in the system, so it shouldn't matter which part of the system I measure really. Okay? So, and also my matrix should not be completely arbitrary, but I should have blocks that repeat themselves because due to equivariance, the action of the operator should be the same everywhere, right? So what I can say is, well, if I know this, I'm not going to learn the 64 by 64 matrix, but instead I'm going to replace it by smaller Q by Q blocks that have to be identical because of the symmetry in the system, right? It's equivalent at the translation, which means all the blocks have to be the same. And so let's have a look at how this looks. If I take Q equal 1, I get basically, well, it's garbage, which is clear because it's a scalar and you cannot have an oscillating behavior using a scalar, right? So, but already at 4, you see that we start to resemble this behavior quite nicely, right? And then if you increase, and as we approach 16, we are close to the original solution again. And so you see, using this additional knowledge, we can even further reduce the measurements we need. We can use partial measurements and extend this to the entire state space and so on. And what people do in this Koopman business usually is look at the eigenvalues and eigenfunctions of the matrix in hope that they resemble what the eigenfunctions and eigenvalues of the operator. And if you look at this and we computed the eigenvalues of these matrices here, these are the 4 pictures, this one, this one, this one, this one. You see then one eigenvalue obviously doesn't do the trick. This is the complex plane now, because it cannot have oscillating behavior. But you see that the larger we make our measurements, the better we approximate the, let's say, leading eigenvalues in terms of the low frequencies. And then it's not surprising that we rediscover basically the wave equation in the end. Yeah, so let's say it's a starting point, but I think the usage of symmetries or the knowledge of symmetries that we have had for such a long time in these learning approaches, this is not my discovery, right? People have been using this in all sorts of learning for a while now, but also here is quite promising to increase the efficiency, to enforce what we know about the system, and so on. Okay, so now I'm going to make quite a harsh change to the reinforcement learning side of things, right? So we have now seen we can use data to learn a linear model or approximately learn a linear model and use this. How about directly learning the policy? Okay, and so I said this is very related, and I'm going to try to make the relation more precise. So in reinforcement learning, what we have is we have an environment and we have an agent, and this agent applies an action to this environment. And by this action, the state changes, right? So what we have is what's called a Markov decision process, which takes state in action and maps to, in a probabilistic manner, to the next state at the next time step. And then what we have is a reward function that we achieve that tells us how well we did with our action with respect to some objective that we have specified earlier, right? And then this reward function basically tells us sort of like the objective function in control, you did good or you did not so well, you should take some other action next time, okay? And so the goal is to find a policy, right? We had this earlier. So directly find a mapping from my state to the actions, also in a probabilistic manner maybe, so that in expectation, we maximize the discounted sum of future rewards. So we look into the future for infinity. Doesn't have to be, you can also use episodic settings with a finite length, but let's say in infinity for now. And we would like to find the policy that if we follow this policy forever, we maximize this quantity. So the value function, if you're more familiar with the control setting. And so here's my attempt to, to link these two viewpoints. So in reinforcement, we have always what we call state. This was simply the PDE state at our example previously. What we call actions is usually known as the control. The Markov decision process is our flow map. And the reward function somehow relates with inverted signs to the objective function value in controls. That you want to minimize an objective function, you want to maximize the reward. And so this value function here is basically our objective function that takes into account the entire trajectory, be it finite or infinite time. But so here's the analogy. And so this pi that we used the optimal control problem for before in MPC is simply now our function that maps state to actions. So this is why I said in the beginning, these are two sides of the same coin. There's no magic to it. It's just a rephrasing basically of what we have been using in MPC. Only difference is in how we learn this feedback law. Now we don't necessarily need a model. We need to learn this pi function directly, or want to learn it directly. Okay, so let's try to do this. Well, I've said quite a bit of this already, but if you know a little bit about dynamic programming, then you will have seen this Bellman equation already. So the optimal value function, the star means this is the best possible value you can get, and choosing the optimal action is by maximizing over all actions to maximize the current reward, plus the optimal value function at the next time step. So it's a complicated problem because it's implicit in the value function, but this is, if you can solve it, you're done, right? And this is what dynamic programming was all about for a long time already. But we have this curse of dimensionality, right? If you do it like in a graph-based manner, you start at all possible final states and then work your way backwards, basically, to see which possible state would be the best action to take. And once you have computed this value function, you're done. However, this quickly explodes in the complexity. This can also be shown if you solve the Hamilton-Jacobi Bellman equations also, then you have the dimension really increases. So it's very, very well known that this is complicated and expensive to solve. Okay, however, if we can solve it, then it's very easy to find the solution, right? If we know the value function here, then we simply have to plug in our model and see what the next step would be, and then maximize over all the A's that we can possibly choose. And so reinforcement learning is nothing else but approximately doing this, okay? So all I'm saying is, if I don't know the true value function V star, then I'm going to introduce an approximation of it, V tilde, and try to iteratively improve my approximation by trial and error. So I try something out, I update my value, and so there's a whole bunch of algorithms. I will not go into all the details, but oftentimes it's really back and forth between the system, you get rewards, and by additional knowledge, you do sort of temporal difference learning, so you iteratively update your knowledge of the value function. And once you're done with the training phase, you can use your model of this value function, which is called the Q function in machine learning and reinforcement learning. But you see the definition of the Q function is exactly this one which you maximize over. And so Q learning is basically finding the value function or the state value function Q. Okay, and now here's the positive side. This is very, very successful in many tasks where you all have seen this, right? Computer games or the Go, beating the best player in Go was extremely popular. Hit the public news as well. There's lots in robotics where people do impressive things with robots and they're trying to walk on their own and so on. However, there's also a drawback. The training can be very, very expensive and also extremely sensitive to different hyperparameters. How do I pick the learning rate? How do I design my network? What I did not say is that what we do, in the slide before maybe, this Q function that we're trying to learn is usually a neural network. As you know, taking S and A, so a state vector and the action vector, and mapping it to a value. And then you can optimize over the Q function to find the best action in every situation you are in. So it's a neural network, and it can be very high dimensional if I have high dimensional state or action spaces. And you can think of the Go board game, obviously you have a large number of states. And so it's expensive, it's sensitive to hyperparameters, because you have to encounter many combinations of state and action to get a good idea of the value function, right? So it has to generalize to unseen states, but to do so, you still need to see a lot of states and action combinations. So, and even if you have to do this with interaction with a real system, right, let's see in the robotics, you have to do a lot of repetitions of the experiments, which can be costly and expensive to really learn a behavior that is successful in the end. And so there is a lot of research, which is rather practical, I would say. How do you define good reward functions? How do you use some sort of what's called teacher forcing, show some good examples, how this should behave and so on to make the training more efficient, right? And so one example, if you know the video game Dota 2, which is a strategy game, OpenAI solved this. So trained an agent that could beat other players, but it took 100,000 CPU cost for the better part of a year to train it, right? So you really have to invest a lot. And so if we think about systems, a bird falling out of the nest learns to fly in the first attempt, hopefully. And so there has to be something that can be done better than, let's say, brute force using a lot of data. And so again, we're back to the PDEs and ask ourselves, can we in the PDE setting use something that we have seen before today, right? So because the setting is the state and the action at any given point in time, or can be infinite dimensional. If you have distributed control, even the action is infinite dimensional. And so if we discretize this into n grid points using finite elements, we have extremely high dimensional states and actions. So the training is virtually impossible. And there are small toy examples of PDEs where you can barely use reinforcement learning to stabilize them just because of the very high dimensions of states and actions. So that they just don't scale that well. And so again, the question that I asked before, can we use something that we know about the system to reduce these dimensions? Okay, and the answer is, again, we have symmetries, right? So in many PDEs, position and time do not show up explicitly, right? So the heating in this room behaves in the same way as the heating would behave in the next room, right? Or back in Paderborn or wherever you are. So the absolute value of space shouldn't matter. So we have, again, this equivariance with respect to translations. And second of all, for many systems, we have a transport of information, let's say mass or energy, with a finite velocity. Okay? If I turn up the heat here, you will recognize this only quite a bit later back in the room, or vice versa. And even in, I think in elliptic PDEs, you have these locality statements that you only have, you have quite a quick decay in terms of distance with respect to what the actions actually do. So let's try to use this. And actually, well, there's in the computer science literature, there's a lot on similar concepts where group equivariant convolution networks in, let's say, image classification. You can talk about multi-agent reinforcement learning, which this is, let's say, also a related concept. So people have started looking into this. And the idea is the following. Now we have this agent that looks at the entire state and be very high dimensional and has to decide on a function a of x, or maybe a discretization thereof, but it could still be very high dimensional. Okay. And now let's not use this, but let's use the observation, the second observation that I posted, that the information is transported with finite velocity. Okay. So basically, if I want to take an action somewhere here in the middle, maybe this state measurement doesn't impact the immediate decision here in a significant way. And so what I can do is I can define this sort of this index set here, which says my local dynamics do not depend on the entire state, but only on a neighborhood, let's say 5 points or so. Looking a little to the left, looking a little to the right, and nothing more. And if I do this and add the second observation, but let's do this for now, maybe in the first step, what I can do is I can replace this global, very large agent, which takes all the states and decides on all the actions, and replace it by local agents that only take, in my example, 5 measurements and decide on a single action. So much smaller agent. And then I can use my first observation. Due to symmetry, all of these agents are actually identical. Okay? So because it doesn't matter where I am absolutely in space, given my measurements, I should decide on an optimal action. And so you see that says obviously massive advantages for training these models, because well, the state dimension is strongly reduced. The action dimension is also reduced, in my case to 1 here. And so these smaller networks for approximating my policy or this Q function become smaller, and you have a massive acceleration in training due to this, because we know something about the system. And actually, there are examples that you cannot train these PDE controllers without using this, but in this way it becomes very easy. And you can share parameters because all of these agents are basically the same. Okay, so this brings me almost to the end. I'm now going to 3 examples to hopefully show you how this works, and then draw a conclusion. Okay, so we're back at the Kowamoto-Zivashinsky equation, but because this is from different works, this is now the dimensional version. So the mu now is not the parameter, but this is just a prefactor before the spatial inhomogeneity, right? If I set mu to 0, I have really equivariance with respect to shift. If I do not set it to 0, I have local dependency, so I lose the symmetry. And then I'm adding this control term, which is there's a sum of these Gaussians to control the system and see what happens. So invariance only for mu equals 0. And what we study is a very simple case. Now, what triggers the complexity is the length of the domain in the dimensionalized version. So 22 is already far beyond what we had earlier, where we had this wave behavior. This is already a chaotic dynamic system with 22 as the length. And so the action, what it takes is you wait for 100 and a couple of seconds, and then decide on 8 of these agents that only look at a small neighborhood. And you see that actually by taking these actions after just a couple of seconds, one can easily stabilize the system to close to the origin, let's say. So it works very nicely, and training can be done on a local computer, this one, in fact, because it's such small neural networks. So all the data doesn't matter, but you see these networks have one hidden layer with 7 or 14 neurons. So it's really, really small agents because they just have to solve a small control problem, basically. However, what we can do now is, because we have neglected the absolute size of our domain, we can simply take the agent and transfer it to a more complicated setting. It's not bound to a specific domain. So what I'm going to do is I'm simply increasing the domain size and increasing the number of my agents without any retraining. And you see that we can still stabilize the system very, very quickly, which you cannot do if you tailor your agent to a fixed domain. Right? You can do this for 500, nothing changes basically. And we did some testing here. If you add this inhomogeneity, which means when you actually do not have the invariance with respect to shift, and you see that the behavior still works rather nicely because these agents tend to be modeled in a stochastic way anyway. So this inhomogeneity in space is sort of, this is my interpretation, interpreted as sort of a noise term. And if you don't make it too large, it still works. If you make it larger, then the agents are not equivariant anymore. Okay, so now we've done this also with more complicated systems. So you have this 2D decaying turbulence model where you have these vortices that decay on their own over time. And we want to apply these mixers locally to stabilize the system more quickly. And so I'm trying to stabilize or rotate here, and I'm looking only at the neighborhood. And if I do it here or if I do it here, doesn't make a difference. So I can apply the same agent multiple times, and you see that depending on how fine I make the grid, you can actually stabilize the system very quickly and again train a feedback controller for such a system on your local laptop because you simply exploit the symmetries, right? And now let me conclude with this example that I like the most, this Rayleigh-Bénard convection that I mentioned in the beginning. It's a very popular system where you have the compressible Navier-Stokes equation and you heat the bottom plate and you cool the top plate. So by convection, you see that you will have cold air dropping down at places and hot air popping up, and you see these plumes. And now the task is to choose actions on the bottom plate. On average, the temperature has to remain, otherwise you could simply set everything to 0 and you stabilize the system, but just find a more pattern that has on average the same heat transfer, but find a pattern that stabilizes the system in terms of minimizing the convective heat transfer. You only want basically reduce it to a heat equation, let's say. And so the heat transport should be reduced, and you can do this with a multi-agent reinforcement learning. So instead of deciding on all these 10 agents at the same time and taking all these points as your measurements, which cannot be done, you take 10 agents that look only at a small region left and right of their own measurement and decide. Right? And then here's a video. There's even a larger domain because you can transfer it again to large. And what you will see, you have 4 of these plumes. It's periodic. And when I started, these plumes will start to merge. Right? So the agent learns to influence the system. And we did not train it to merge these. I think it will start right at the boundary, but it will happen twice. So that here's this heating pattern on these local agents, and you see that they actually learn to merge these plumes, because apparently this is, I think it will happen the second time in the middle, I believe. This is more efficient in terms of reducing the heat transfer by convection. And so you see again, you can train these expensive problems if you know something about the system. Okay, so this brings me to the end of my talk. To summarize, there were two paths, rather distinct, but I guess the overarching idea is control using data and system knowledge. So the Kuhlmann operator is very efficient because it's linear regression, basically. But if you work a little, you have guarantees that are stronger than what you have for neural networks. And there's lots to do, but still, we're still already today, one can do really cool things with it. And the second time, even in reinforcement learning, where we directly learn the policy, using system knowledge, again, in the form of symmetries, is really advantageous for sample efficiency, right? And as a small outlook, the details don't really matter here, but what we also did is we used a different learning algorithm, what's called extreme learning machine, instead of the Kuhlmann operator. You don't have to stop at translation and equivariant. This is a 2D Kuramoto-Zibashinsky equation. And you see, obviously, you can also use rotational symmetries to even further reduce the training data, but I'm not going into details. All right. Well, finally, combining these two might be an interesting road to take to train a reinforcement learning on a data-driven model instead of the real world. Well, but model-based reinforcement is not news. People have been doing this, but not with the Kuhlmann operator, I would say. Okay, thanks a lot for your attention, and I'm happy to take your questions.